Okay, good morning. So, in the last lectures up to now, we looked at one actual functional programming language, Haskell. And starting from this lecture, we will look at the background behind functional programming. So, at the theory that is behind functional programming. So, in other words, so what we had was, well, we had the introduction to Haskell, and in this first introductory chapter, you got to know all kinds of special features of functional languages. And now we look at the theoretical background. And the first thing that we look at is the semantics. So this is what we're going to do now. And the semantics determines the meaning of programming languages. So what we determined formally was the syntax of Haskell. So we gave a grammar saying, well, a Haskell program is a sequence of declarations, and then we had rules saying what declarations are. Declarations consist of certain things, including expressions. Then we had rules defining what expressions are, and so on. So in this way, you can determine the syntax. But in order to determine the semantics, so here in particular, we determined the syntax by giving suitable grammar rules. But, well, of course, we also said intuitively what these constructs of the programming languages mean. But to determine this formally, you have to determine the semantics. And we will do this now. And the semantics we will give is a denotational semantics. So why do we do this? Well, we determine formally what do the constructs of the programming language mean, and why is this useful? Well, this is needed in order to determine, for example, what a program actually does. So if you want to say your program is correct or not, well, then you need to know what these constructs mean. So, for example, we have a construct if, then, else. Now, intuitively, you know what if, then, else means. It means if the condition is true, then do the thing that comes after then. And if it's not true, then do the thing that comes after else. But somehow you have to determine this formally. And there are more complicated constructs in Haskell than if, then, else. So you somehow have to write this down formally in order to determine what a program actually does. And you need this for, well, you need it for verification. How can you say that a program is correct if you don't know what the constructs actually mean? But you also need this if you want to implement a compiler or an interpreter for the language, because your compiler has to execute the program in a certain way. And you don't want that one compiler executes your program in a different way than another compiler. I mean, these compilers may differ in efficiency, but they should do the same thing. And so you have to determine what a program actually means. So it's needed for implementing Haskell by compilers or interpreters. And as I said, the semantics that we will define is the denotational semantics. And denotational means we simply define the semantics by a function which goes from Haskell expressions. So we do this all for Haskell. So Haskell is the example language that we look at in the lecture. So we will continue working with Haskell, and we will define the semantics of Haskell. So we do this by defining a function which goes from Haskell expressions to certain mathematical objects. And this way of defining a semantics is called denotational. So denotational means define the semantics by giving just a function or a mapping from Haskell expressions to mathematical objects. So, for example, there's a Haskell expression 1, the number 1, and we will map this Haskell expression to a mathematical object, namely the number 1. Now, this mapping sounds rather easy, but sometimes it's not so easy. So we will see that this is not completely straightforward. Now, this is not the only way to define the semantics. maybe you have already seen definitions of semantics, but then the semantics is usually defined in a slightly different way, namely by means of an operational semantics. And we will do this as well, because after defining the denotational semantics, we will discuss the question, how can we actually implement Haskell? Now, as I said, if you want to implement a programming language, then you need to know the syntax of the language, but you also need to know the semantics, because otherwise you don't know what the language should actually do. And to implement it, we will introduce a very basic functional programming language, the lambda calculus. This is a very, very basic functional programming language. So the syntax of this is very, very easy. So you can learn this immediately. And the semantics of this is also very, very easy. And we give the semantics of the lambda calculus defining a denotational semantics for the lambda calculus is also possible and much easier than for Haskell, because Haskell is a much richer language. But here I will only give an operational semantics, which is also very easy. And in this way, we can also define... Now, operational semantics means define the semantics not by giving a function from expressions to mathematical objects, but by giving an interpreter and saying, this interpreter implements my language, and every other interpreter that does the same thing is correct. So basically, operational semantics is you define the semantics by giving one standard implementation of an interpreter and by saying, what this interpreter does, this is the semantics of my language. So here you define the semantics by giving a kind of interpreter for the language. And in order to implement Haskell, what we will do is we will show how to translate full Haskell, or almost full Haskell, into this very basic functional programming language, the lambda calculus. And then this can be implemented by simply taking this interpreter, which executes this lambda calculus. So in this way, we obtain an implementation in that way, in a compiler or interpreter for Haskell. And then finally, the last section that we will look at will be devoted to type checking. So in the next two sections, section 2 and 3, we will assume that all programs are well typed. So there are no type errors. We will assume this in section 2 and 3, and then in section 4, we will come back to this and we will discuss how to check whether your program is actually typed correct. So once you've checked that your program is well typed, there are no type errors, then you can do what we discuss in section 2 and 3. So in section 2 and 3, we will assume that our Haskell programs are well typed, there are no type errors. And how to make sure that there are no type errors we will discuss in section 4. Well typed. Or type correct. Okay, so let's start with the semantics. And so this is chapter 2. The semantics of functional programs. Okay, and as I said, semantics, we want to define a denotational semantics, which gives us a mapping from Haskell expressions to mathematical objects. And the question is, what mathematical objects do we use? Now, okay, if we want to map objects of type int to mathematical, so expressions of type int, we would like to map them to integers. Expressions of type Boolean, we would like to map them to Boolean values. But to define the domain of those mathematical objects that we use for the semantics, to define this formally, we need some kind of mathematical background. And this is what we're going to do in section 2.1. So here we introduce the mathematical background. Which is needed to define the semantics. And then in section 2.2, we define the actual semantics. So here we define the denotational semantics of Haskell. And then we have formally defined what a Haskell program means. Now, up to now, we always gave intuitive explanations saying, well, this means that, and you can program with this intuitive explanation, but then still, there are some cases where, well, you don't really know what the program does. You just try it out in your interpreter. But if you want to write an interpreter, you cannot try it out. Then there has to be some kind of formal definition. Okay, so the mathematical background that we need is concerned with complete partial orders and with fixed points. And this is section 2.1. So we need to know something about complete partial orders and about fixed points. Okay. Now the main problem is, as long as we have expressions like the number 1 or something like this, it's pretty clear which object we are going to map it to. But the problem appears as soon as we have things where things are undefined. I mean, in Haskell you can write functions that don't terminate. Now, what value do we want to assign to expressions which contain undefined parts? For example, you can have a list where first element is, say, 1, and the second element is some kind of function which doesn't terminate. Now, what value do we want to assign to this Haskell list? That's not so clear. And therefore, the first thing we have to look at is how do we deal with these partially defined values where, well, the value is a bit defined but also a bit undefined. What do we want to do with this? And that's the first subsection. What do we do with partially defined values? Okay. So as I said, the semantics will be defined by some kind of function, by a function, I call it val for value. And basically what this value function does is it takes an expression, so this is the set of Haskell expressions, this is the set of Haskell expressions, and it maps every Haskell expression to some mathematical object. For example, a number or a list of numbers, something like this. So, to some kind of domain, and this is a domain, and what I mean by this is it's a set of mathematical objects, including, for example, numbers or lists of numbers or booleans and some other things as well. So, it's a suitable set of mathematical objects. How this domain will look like exactly, we will see it later. Okay, so how should this function look like? Well, for example, if we have the Haskell expression 5. So this, you can write 5 is a Haskell expression. You can type in 5 in your interpreter. You press return. And what should the meaning of this Haskell expression be? Well, the meaning of this should be the number 5. So this is an integer number. So this Haskell expression, the syntactical expression, should have the semantics number 5. Now this is not surprising. Maybe another. What should happen with an expression like this? Now assume square is defined like this. So let me define square. So square should be a function from int to int, and we define it as usual. So square of x should be x times x. Well, this is the first idea. How do we do here? Now, square is again a Haskell expression. It's a variable, but this variable has a certain meaning because there's this equation over there saying that square of x is x times x. So what should the value of this Haskell expression be? Well, it should not be a number. It should be a function. It should be the function from integers to integers which squares numbers, so which takes a number and gives us back the square of the number. So this should be the function on integers which basically computes the square of a number. So it's the function, if you give 5 to this function, you get back 25. Now, in Haskell, not all functions have to terminate, like in any other language. So if we write a function like this, non-term, which goes from int to int, and non-term is defined like this. So non-term of x should be non-term of x plus 1. And then the question is, what should the value of non-term be? Now, obviously, it should again be a function, but what function should it be? It should not be the function that squares integers or that doubles integers or the identity function. Now, that's not a good idea. So the question is, what do we want here? Well, intuitively, what we want is that this function should always be undefined, because non-term doesn't terminate. No matter what argument you give to non-term, you get no result. The result is undefined. And in order to model this, in our domain, it's not sufficient just to have integers and to have function on integers, but we also need some kind of handling undefinedness. And to handle undefinedness, we introduce a special element which stands for undefined. So this is a function on integers which maps every number to the value for undefined, and the value is denoted like this. So it's a capital T upside down, and that stands for bottom. So this is pronounced bottom, and this is a special value which stands for undefined. For undefined. So if we think about the domain, if we think about what mathematical objects do we need, so the domain needed for our semantics should therefore include things like the integer numbers, but also values like bottom for undefined. It should include functions. And then if we have another expression, for example, the tuple consisting of 5 and 7, this will be mapped to a tuple of integer numbers. So it should also include things like tuples. It should include things like lists and so on. Now, of course, our programs are typed. And therefore, it makes sense to also to distinguish between these types when we define the domain. So expressions of type int should be mapped to certain elements of the domain, and these are different elements than those elements that expressions of type bool would be mapped to. And to make things easy, let us first exclude polymorphic programs. Haskell has polymorphism, as you know, so you can use type variables, and an expression has many types, and there is one most general type, for example, some type containing type variables. But to make things easy, at the moment we exclude polymorphism and just treat Haskell as if there were no polymorphism. So since Haskell has types, for every type, let's say for every type tau, there should be basically a separate domain, let's say dom tau, and then expressions of type tau are mapped to values from dom tau, and the whole set dom is just the union of all these dom taus. So expressions of type tau are mapped to values from dom tau, and then dom would just be the union. Whenever tau is a type, then it would be the union over all dom taus. And to make things easy, as I said, so first only regard so-called monomorphic types. Monomorphic is the converse of polymorphic, so this means no polymorphism, no type variables. No type variables. And then every expression has one unique type. Now in reality that's not true because, for example, 1 doesn't have the type int, but it has the type a, where a has to be a type from the type class num. So it's num a double arrow a. But to make things easier, at the moment we exclude polymorphism and say then every Haskell expression has a unique type. Okay, and for every type tau, we now define a corresponding domain, dom tau. And then expressions of type tau are mapped to mathematical objects from this domain, dom tau. And now we look at one type after another and decide how this domain for this type should look like. Okay, how would the domain for expressions of the type int look like? So I mean, in Haskell we have some base types. These are the predefined types like int, character, boolean, and so on. So let's start with int. We have seen that the Haskell expression 5, we would map to the integer number 5. So first idea would be we take the integer numbers. Sure, this one. Okay. So the first idea would be maybe we should, what is the meaning of Haskell expressions of type int. First idea would be, well, every Haskell expression of type int, the meaning is an integer number. Do you think this is a good idea? Or do we need more? Can you think of an Haskell expression of type int where the value is not 1 or 2 or -1 or -2 or 0, but something else? When you think of this, yeah. Square root, if you take square root of, say, 2, then what comes out is not an integer number. It's a floating point number. And, I mean, we also have to have a domain for expressions of type float. And there, of course, we would take something like the rational numbers and not the integer numbers. And that's not a problem. I mean, obviously, expressions of type float, we don't want to map to integers. We want to map to rational numbers. Now, that's okay. But if you think of non-term 0, non-term 0, non-term is up there, non-term 0 is a Haskell expression of type int. Now, to what integer number do you want to map non-term 0? To 17? No. To 0? No. Oh, you need one more object. You need something for undefined. Non-term 0 is not defined. Still, it's an expression of type int. So you have to map this expression to some mathematical object, and you don't want to use any of these integers, so you need an additional object, this bottom object. So z_bottom is a special value for undefined, and this is the undefined value of the integers. So the undefined integer is something different from the undefined Boolean. And apart from that, the rest are the integer numbers. So 0, 1, -1, 2, -2, and so on. And then indeed, the value of non-term 0 would be this. It would be in this domain, because this is an expression of type int, but it's undefined, so it should be this. The value of square 5, on the other hand, should be the number 25. This is really the integer 25. Okay, and we simply do it like this for all base types. So the domain for expressions of type Boolean would simply be this set, which contains not only true and false, but also a bottom value which stands for undefined. Because obviously, you can also write Boolean expressions where the evaluation should not terminate. So you have a value for undefined, and you have true and false. And similarly for other base types, like character or floating point numbers, and Haskell has a few more. So you simply take those objects that you would normally take, plus an additional object for undefined. Now, these domains, this one and this one, they are very easy. They have one undefined value and many other values which are completely defined. Now, not all domains are as easy as this. And in particular, if you think of something like tuples or lists, it can happen that some components are defined and some other components are not defined. Now think of a tuple with 3 components. The first one is 0, the second one is 1, and the third one is undefined. Now this is not completely undefined because the first 2 components are defined, but the third one is not. So it makes sense to compare elements of this domain by their definedness. Some objects are more defined than others. Now in these very simple domains, they are called flat domains, something is either completely defined or not defined at all, but in more interesting domains, it's more complicated. So to compare elements of a domain by their definedness of a domain D, by their definedness, we introduce a relation which is usually denoted by this less or equal, but as a square. And this means less defined or equal. Less defined or equal. So, in other words, if x and y are elements of a domain, then this means x is less defined or equal to y. So this means x is less defined or equal to y. And of course, if you omit this dash here, this underlining, then you can also have strictly less defined. Now, in the domains that we had up to now, so domains like z bottom and b bottom are called flat, and flat means there is one undefined value and everything else is defined. So one value is completely undefined, everything else is completely defined. So we would, for example, have the following. The undefined value of z, oh sorry, I forgot the bottom here. So in this index, this here is z bottom. So this is the undefined value of the set z bottom, not of the set z, because z doesn't have a bottom. And here again, this is the undefined value of b bottom. So I forgot a bottom over here. So the undefined value of z bottom is obviously less defined or equal to 0. This is less defined. This is not defined. This is undefined, and this is defined. So this is less defined than 0, but it's also less defined than 1. But do you think this is also true? 0 less or equal than 1. Do you think this is true? Is 0 less defined than 1? No. 0 is completely defined, 1 is completely defined, so they are incomparable. So this is not true. And similarly, 1 is also not less defined or equal than 0. They are incomparable. So if you want to depict this in a nice way, you can say, okay, this thing is the smallest element. It's the smallest element with respect to this relation. So it's the thing that is as undefined as possible, and everything else is more defined. So 0 is more defined, minus 1 is more defined, 1 is more defined, minus 2, 2, and so on. Now these things means this is greater than that, and this is greater than that. But 0 and 1 are incomparable. It's not that 0 is undefined and 1 is defined. They are both defined, but they are not equal. And therefore they are incomparable. And this is called a flat domain because, well, either you have something which is completely undefined or you have something which is completely defined. And if we know about which domain we are speaking, then we sometimes omit this index here and here. So index is omitted if it's clear from the context. Okay, so at the moment we have this relation. We can compare objects by their definedness, and well, in those simple domains that we know up to now, something is either defined or undefined. So bottom is less or equal than everything else, and the rest is not comparable. Okay, let's think about the properties of this relation. So, what does this less defined or equal relation, what properties does it have? Now, one property it has is reflexivity. So, in other words, x is always less defined or equal than x. So, in our example, if we look at z bottom, then bottom is less defined or equal to bottom. 0 is less defined or equal to 0, 1 less, they are equal. This means less defined or equal, so if it's equal, then the relation holds. Now this relation has two more interesting properties. The other property is transitivity. Transitivity means if x is less defined or equal than y, and y is less defined or equal than z, then x is less defined or equal than z. Okay, this property clearly holds because if we have this x less defined or equal than y and y less defined or equal than z, then if they're not equal, then the only possibility is that x is bottom and y and z are equal, or x is bottom, y is bottom, and z is something else. And in any case, then we would have x less or equal than z. So for our flat domains, this is clearly true. And the third property is called antisymmetry. And antisymmetry means if x is less defined or equal than y, and y is less defined or equal than x, then this means x and y are equal. So, if x and y are not equal, then it can't be that x is less defined than y and y is less defined than x. That's not possible. So the only way that this can hold is if x and y are equal. And every relation which has property 2 and 3 with property 2 and 3, so relations that are transitive and antisymmetric are called orders. So this relation here is a reflexive order. Okay, and this is a very nice property we want. When we look at more complicated domains, we had these very simple domains up there, but when we later on define more complicated domains, we again want that this relation is a reflexive order. So we will make sure that reflexivity, transitivity, and antisymmetry still hold. Okay, let me put this into a formal definition. We have defined these flat domains for base types like integers and booleans, but also characters, floating points, and so on. And this is definition 211, which defines how this relation looks like on base domains, so on domains for the base types like integers and booleans. So let D be a base domain, and what I mean by this is something like Z bottom, which is the domain for int expressions, or B bottom, which is the domain for bool expressions, or also C bottom. C is the set of characters. So C bottom are all the characters. So it's a bottom element of C bottom, and then it's the character A, and the character B, and the character C, and so on. Or F bottom, and F bottom is the domain for floating point numbers. So there would be a bottom element, and then we would have something like 1.0, 1.1, 1.12, and so on. And then we define the following thing. We say for all objects D and D prime, D is less defined or equal than D prime if and only if. So this if with two F's is a shorthand for if and only if. This means if and only if. In German, it's genau dann wenn. So if and only if either D is the bottom element or D and D prime are equal. And such domains where you just have one thing that is completely undefined and everything else is completely defined, such domains and such orders are called flat. So it's a flat domain and a flat order. Now, okay, these are the very simple domains. Now let's look at more complicated ones. We have discussed if we have expressions of type int or boolean or character or float, what we do with them. Now what happens if we have expressions of a tuple type? So definition is over. How do we handle expressions of tuple types? So what should be the value, say, of the following expression? Is the tuple consisting of the number square 5 and non-term 0. So what do we want here? What do we want that? I mean, this is an expression of type int, and this is also an expression of type int. So the whole expression has the type int, comma int. So this whole thing has the type int, comma int. And well, what we will do is we will map this again to a tuple. I mean, tuple is also a nice mathematical object, so it will be mapped to a tuple of two values. And how do we get these values? Well, the first component will be the value of this, and the second component will be the value of this. So the outcome will be the value of square 5, which is 25, and z bottom, which is the value of non-term 0. Now, this thing is a tuple, so this comes from z bottom cross z bottom. This is the Cartesian product that you know in mathematics. So in order to handle tuple expressions, we will also look at domains that we get from existing domains by building the cross product. And, well, now this thing is not completely, so this is an element of this domain. It's not completely defined and it's not completely undefined. The first component is defined, the second one is not defined. Now, obviously, you might have things like, so this is 25, and here we have, so I omit, as I said, I omit this index, the subscript, when it's clear from the context. So this is an element of this set. Now, obviously, this is also an element of this set, and 25, 17 is also an element of this set. So these are all elements of the set z bottom cross z bottom. Now this is very undefined because both components are undefined. This is a bit more defined because the first component now is defined, the second one is still undefined. And this one is even more defined because now both components are defined. So this here is less defined in Z bottom cross Z bottom. This is less defined or equal than that, but this is less defined or equal than that. And now you can see, well, now this relation beginning, and this is not a flat domain, because now we have this chain of length 3, because this is less defined than that, but this is again less defined than that. So things can become more and more defined. And we can define this formally again. So if we have some domains, we can build their cross products, and then we get another domain. And this less defined or equal relation can then be defined on these product domains as well. Okay, so let's assume we have several domains, d1 to dn. And to make it interesting, there should be at least 2. So n is greater or equal than 2. And then the cross product d1 cross dn is also a domain. And how do we define this relation? We define this relation on, so the less defined or equal relation on this domain is defined as follows. Now the elements of this cross product domain are tuples consisting of n components. So small d1 comes from domain d1 and small dn comes from domain dn. And when do we say that this thing is less defined or equal than a tuple d1 prime until dn prime? Now, what would be your suggestion? If you look at this example up there where you see, well, if we switch one component from bottom to an actual defined value like 25, then the definedness of the whole tuple increases. Now, how would we define this? I mean, we have the relations less defined or equal for d1 to dn, and now we want to define this relation also for the cross product. Mm-hmm. If it holds for each of the components. Exactly. So we want that di is less defined or equal than di prime for all I from 1 to n. This is exactly what happens up here. So there, bottom is less defined or equal than 25 in the first component. In the second component, bottom is less defined than bottom. And, well, if we define it like that, then it's clear how the smallest element looks like. So the smallest element with respect to this relation is therefore the tuple where everything is undefined. So it's bottom d1, bottom d2, until bottom dn. And we also denote it as the bottom element of this new domain d1 cross dn. Okay, so let's look at an example. So this was the situation for these flat base domains, like Z bottom or B bottom. Here we had one smallest element with respect to this definedness relation, and this was smaller than 0 and 1 and minus 1 and 2. And all these numbers here, all these defined values are incomparable. Now when we have tuples, this is more interesting. For example, if we look at this domain, z bottom cross z bottom. So these are pairs of numbers, or, well, in each component you have something from z bottom. So it's an integer, or it's the bottom element of the integers. So the smallest element would be bottom bottom. If you want to have something bigger, then you have to change bottom, one of these bottoms, to a real, to an integer number. So for example, if you change the first component to 0, you get bigger. If you change the first component to 1, you get bigger as well. And similarly for 2 and 3 and so on. So this is not the whole story. This thing is, of course, infinite. There are infinitely many integers. If you change the second component, then you get also bigger. So the tuple 0 bottom is bigger than bottom bottom. And the tuple bottom 0 is also bigger than bottom bottom. But these two things are incomparable. These are incomparable because in order to compare them, each component would have to be smaller. 0 would have to be smaller than bottom, and bottom would have to be smaller than 0. Now 0 is not less defined or equal than bottom. And then from here you can get bigger by exchanging the second bottom by a defined value, for example by 0 or by 1, and similarly here. So you get a structure which looks like this, and you can see now if we have tuples with two components, then these change where you get more and more defined can have length 2. Obviously if you have tuples with 5 components, these chains can have length 5. So it's not flat. There are things that are completely defined, there are things that are completely undefined, but there are also things in between. And, well, we had this nice property of this defined, less defined or equal relation. We had these nice properties for base domains, namely it's a reflexive order. Now this also holds for product domains. And that's lemma 213. And lemma 213 says, if all these relations for d1 to dn, if they are reflexive orders, then the relation less defined or equal on the product domain is also a reflexive order. So what one has to prove is, one has to prove that it is reflexive, it is transitive, and it is antisymmetric. And that is not difficult, and therefore this is one of the exercises on the next exercise sheet. I will do a similar proof like this in a minute. Because we don't only have, I mean, now we know what to do with objects of these base types like int and bool. We know what to do with objects of tuple type. Now the next interesting thing is, what do we do with objects that are functions? And then how do we compare functions? When do we say that a function is less defined than another function? Now somehow non-term should be less defined than square. I mean, non-term always gives us something undefined. Square terminates always and gives us the square of a number. So non-term should be smaller than square, for example. How do we do this? Okay, so how do we deal with functions? Well, we have already seen square. So the expression square we want to map to the function on integers which takes an integer and squares it. And so we also want to regard not only tuples of domains or combining domains by cross product, but if we have two domains, d1 and d2, we also want to look at the set d1 arrow d2, so all the functions from domain d1 to domain d2. And we can lift this idea to these functions as well. So this is definition 214, and here we now define this less defined or equal relations on functions. So if we have two domains, d1 and d2, and we have two functions, f and g. So f goes from d1 to d2, and g also goes from d1 to d2. And now the question is, how do we define less than or equal on these on these functions? So formally, the set of all functions from D1 to D2 is not a domain, and the reason is that, I mean, there are many, many functions from D1 to D2. So let's assume D1 is Z bottom, D2 is also Z bottom. So then these would be all functions from Z bottom to Z bottom. And the problem is there are a bit too many. For example, not all of these functions that are in the set are computable. Now, we are only interested in computable functions because what we want to do is we want to define the semantics of a programming language. Now, I mean, for every integer, you can write a Haskell expression which computes this integer, at least in theory. I mean, in practice, maybe integers are limited somehow, but in principle, you can write down an integer expression which corresponds to this integer value. Now, with functions, this is not true, because there are some functions that are not computable, so there is no computer program that can compute this function. And so for certain functions, there is no corresponding Haskell expression which would have this meaning. And it's not a good idea to include all of these nasty functions that are not computable in this domain. We will later on define this domain for functions, and this will be a subset of this. So it will only contain some functions, but not all of them. In particular, some of the non-computable functions will be missing. So it would include for example, non-computable, also nicht berechenbar, non-computable functions which would not correspond to any Haskell program. So the domain that we really use for functions, we will look at this in the next subsection. So the domain for functions will be a subset of all these functions. And we will see this in the next section. This is section 212. Okay, nevertheless, although this is not we will not use this as the domain for function, but just a subset of this, we can still define this relation for comparison on all these functions. So when do we want to say that a function f is less defined or equal than a function g? Now, for example, non-term is less defined than square. And, well, we do this simply by comparing the function on all arguments. So we define that the function f is less defined or equal than g if f of d is less defined or equal than g of d for all arguments d. So d comes from d1, small d comes from d1, and here we get objects of set d2, so here we need to compare these results by the less defined or equal relation of capital D2. So this means the results of G are always more defined than the results of F. And that, or more defined or equal than the results of F for all arguments. And what is the smallest element? Which we denote like this. So what is the smallest element? The smallest function from D1 to D2. We denote this function like this. Now this must be this is a function. So this is a function from D1 to D2, and it should be the smallest function. So what does it do? How does it look like? If it's a function from D1 to D2, we can apply it to elements of D1. And then what will be the result if this is the smallest function? It will be bottom, exactly. So the result of this will be bottom for all D from D1. So the bottom function, the function that always returns bottom is the smallest one. So for example, we now know that the value of non-term, in fact, is the smallest function. So it's the smallest function which goes from z bottom to z bottom. It's the function that returns bottom for every argument. And, well, of course, this function, so, and therefore the value of non-term is the smallest function, and therefore the non-term function is smaller than the square function, for example. But now you can also see that now we can get more and more defined functions, and we don't just have chains of length 2, but we can have chains of arbitrary length. I mean, we can have chains like, assume we have, so f0 might be, let's say we have functions which look like that. So f0, all these fi's go from z bottom to z bottom. And then let's say f0 of bottom is bottom, f0 of 0, and f0 of x is x for x is 0, and otherwise it's again bottom for x. So this would be defined only for 0 and undefined everywhere else. Now f1 could be something which is again bottom for bottom. f1 of x is x for not only 0 but also 1. And f1 of x is bottom for all other x's. And then f2 of bottom is bottom, f2 of x is x for x from 0, 1, 2, and otherwise. And so on. So this thing is defined only for 0. This thing is defined for 0 and 1. This thing is defined for 0, 1, and 2, and so on. So we may have infinitely many functions, f0, f1, f2, f3, f4, and so on. And they get more and more defined. And on those values where they are defined, they do the same. So f0 of 0 is 0. f1 of 0 is also 0. f2 of 0 is also 0, and so on. So on the value 0, they all do the same. On the value 1, well, on the value 1, this is undefined. This one gives us 1 on value 1. This one gives us 1 on value 1. And the other ones give us 1 on the value 1 as well. So what we have is, we have f0 is less defined or equal than f1. This is less defined or equal than f2. This is less defined or equal than f3. And so on. So this is an infinite chain. Things get more and more defined. But if we take any of these functions, fn, at some point fn, they are defined, fn will be defined for 0, 1, 2, 3, 4, 5 until n, but it will be undefined for n plus 1, n plus 2, n plus 3, and so on. So we get more and more defined, but this will never stop. So now you see that this relation becomes more and more interesting. It's not just that we have things that are undefined and things that are defined. It's not just that, well, okay, things can get a little bit more defined, but after 2 steps, we have everything defined. Now we have things that get more and more defined, and it takes infinitely long. So you can get more and more defined infinitely often. So this is an infinite chain, and values get more and more defined. Get more and more defined. But even for such functions, this less defined or equal relation is still a reflexive order. So we have a similar lemma as before. And the lemma says if the less defined or equal relation of D2 is a reflexive order, then this relation from D1 to D2 is also a reflexive order. Okay, and as I promised, I will illustrate how to prove something like this. So one has to prove three things: reflexivity, transitivity, and antisymmetry. I will only prove transitivity, the rest is the same. So I will prove transitivity. Now transitivity means the following thing. Assume we have f is a function from D1 to D2. F is less defined or equal than G, and G is less defined or equal than H. And now the goal is to show that then F is less defined or equal than H. Now this means, by definition, that for every argument, small d from D1, for every argument, small d, F of d is less defined than G of d, and G of d is less defined than H of d. So this means F of d is less defined or equal than G of d, and this is less defined or equal than H of d for all d from D1. Okay, and do you have an idea how to continue? I mean, we want to show that F in the end is less or equal than H. So we want to prove that this relation here is transitive. Mm-hmm. Because we know that this relation is transitive. So that's the prerequisite. This relation must be a reflexive order. So an order is transitive, so this thing is transitive. Exactly. So by transitivity of this relation D2, we know indeed that F of D is less defined or equal than H of D. Again, for all D from D1. And by definition, this is the same thing as F is less defined or equal than H. So this is indeed not very complicated to prove this. And antisymmetry and reflexivity work in the same way. And therefore, I don't show you the proof. So antisymmetry and reflexivity, they work analogous. Okay, so we've now an idea how to deal with these partial values, and we have an idea how to compare objects where something is partial. Okay, so this is the function domain. Now, as I said, with functions, things are a bit more complicated. We don't want all functions in the domain. So not all functions from D1 to D2 can be the meaning of a program. Only certain ones are allowed. And the next subsection is devoted to defining which functions we really use when we define the semantics. And those functions that we really use for the semantics are monotonic and continuous. Continuous, in German this means stetig. Monotonic and continuous functions. Okay, and the goal is we want to define which functions from a domain D1 to another domain D2 can be used when defining the semantics of Haskell. Now, all the functions that we use for defining the semantics are total. We have this special value bottom, which we use to model undefinedness, but then all the functions are total. So they're, for example, total functions from z bottom to z bottom. They might return bottom for certain arguments. That's okay, but they're still total. So we only use total functions. But nevertheless, these functions, of course, may have the result bottom. But functions may have the result bottom, of course. And since we need to deal with this bottom element, very often we have to extend functions that we already know, for example, functions on the integers, we have to extend them in order to work on z bottom. So since our domains include this bottom element, functions, existing functions often have to be extended to operate on this bottom element or bottom argument on bottom as well. And this leads to the following definition, which I will show you as soon as I have wiped the board. Okay, so I define what it means to extend functions. This is definition 216. So this is about extension of functions. And I also define what it means to be strict. So some functions are called strict. And this is related to the question of extensions. So suppose we have some function f, which goes from some set A to some set B. And an extension of f is a function which does not only operate on the set A, but it operates on the set A bottom, which contains one additional element, bottom. So any function f prime going from A bottom to B is an extension of f if the following holds. It's an extension of f if A bottom is simply A united with an additional element bottom. Bottom of A bottom, so it's a kind of smallest element of this A bottom. And this f prime has to be the same as f for all elements of A, but what it does on this new element bottom is arbitrary. So fd is the same as f prime of d for all d of the element A. So f prime is the same as f, but in addition to f, it also operates on this bottom element. And what it does on this bottom element is not determined. So it can do anything on this bottom element. And now one option, of course, is that as soon as you apply a function to this new element bottom, it should also return bottom. So this is something you can do, but you don't have to do. If you do it like this, then such a function is called strict. So a function g, which goes from d1 to d1 cross d1 cross dn until which goes to d for domains d1, dn, and d, is called strict. If the result of G is bottom whenever one of the arguments is bottom. Whenever di is bottom for some I from 1 to n. And otherwise it's called non-strict. G is non-strict. Okay, let's look at an example. So here's again the definition, saying that, okay, now it's called f, I wrote g, but the definition says a function is strict if, basically, as soon as one of the arguments is undefined, then the result is also undefined. That's what strict means. So if one of the arguments is undefined, then the result is undefined. Maybe should I write this down? So strict means if some argument is undefined, then the result is undefined. Okay, let's look at an actual example, the following Haskell program. So this program maps integers to integers. It's called 1, and the reason is that it maps every integer to 1. So 1 of 0 is 1, 1 of 1 is 1, 1 of 2 is 1, 1 of 3 is 1, and so on. So the question is now, what should the semantics of this program be? So we will map this 1, this Haskell expression 1, to some object. So the value of 1 will be some object which is a function from z bottom to z bottom. Now what this function does on z is rather clear. So as soon as you give, this function here is some function called, so val of 1 is some function f. Val of 1 is some function f, and obviously f of x must be 1 for all x from the integers. In order to somehow reflect the semantics of this Haskell program, it should be mapped to a function f, which gives us 1 for all integers. The question is, what happens if we apply f to bottom? How should f bottom be defined? So, we have to, the meaning, the semantics of an expression of type int to int must be a function from z bottom to z bottom, so it's a function that you can also apply to bottom. So this f must be a function, well, if you apply it to integers, it should be 1. If you apply it to something else, if you apply it to bottom, then it also has to have some result, and the question is what? Now, why is this interesting? Well, imagine you look at this expression. 1 applied to non-term 0. Now, this is a legal Haskell expression. Clearly, you can write this down. This is an expression of type int. So if you apply 1 to an expression of type int, you get again an expression of type int. Now the value of this thing, the value of non-term 0 is in fact bottom. So this will be, if the semantics of 1 is this function f, then the semantics of this expression val applied to non-term 0 is function f applied to bottom. So we need to define this because this really occurs in practice. We can write down expressions where the expression 1 is applied to another expression and the value of this other expression is bottom. And so we somehow have to define what should happen now. Okay, let me make 3 suggestions how we can define, how we can answer this question. So how would we define the semantics of 1 if it's applied to something which is undefined? So here are 3 proposals. Okay, so 3 proposals. Do we want to take f1 as the semantics or f2 or f3? Now, if we apply them to integers, they must give us the result 1. Now, there is no choice because we really want to define this in a sensible way. If we define something like this, then clearly for every integer it should give us 1. But what happens if we apply the function to something which is undefined? And now I made 3 proposals. First proposal says, well, if you apply this to something undefined, then also return 1. Next proposal says, well, if you apply to something undefined, then the result should be undefined. And the last proposal says, if you apply to something undefined, then the result should be something different. Not 1, but 0. Or whatever, 5. Now, what do you think is the semantics we should choose? Mm-hmm. Yes, and why?
Because Haskell is lazy, and it will not even start evaluating non-term because it will see that it doesn't matter.
Right, exactly. So this is the correct reason. Indeed, when we want to define the semantics of Haskell, we will choose version 1. Because, as you correctly said, Haskell has non-strict evaluation, and somehow this has to be reflected in the semantics. The semantics must make clear that even if the value of x is not defined, 1 of non-term, I mean, if you type in this into your interpreter, and you press return, you get 1. This will be defined because Haskell does lazy evaluation, outermost evaluation. So this version, version A, would correspond to this lazy or non-strict semantics, and this is what we are going to do. Now there are other programming languages which don't have lazy evaluation, but innermost evaluation. For example, ML or Lisp, but also all imperative languages, they would do this. They would first evaluate their argument, and if the argument is undefined, then the whole thing will be undefined. So this is also a sensible way of defining the semantics. It does not capture the semantics of Haskell, but if we would look at a different programming language, this would also be a good idea. So we need version A. We use A because Haskell does non-strict or outermost evaluation. And as you can see, this function f1 is not strict. f1 here has an undefined argument, but still the result is defined. Now in functions with innermost evaluation or eager evaluation or call by value evaluation, this can never happen. As soon as some argument is undefined, the result is undefined. So in languages, programming languages with call by value evaluation or innermost evaluation, one would use B. And examples for this would be functional languages like ML or Lisp or Scheme. And what about C? Do you think there can be another programming language where you would use variant C, where, this would mean if you execute your program, then first the program has to determine whether the argument is defined. And if it's defined, it returns 1, and if it's not defined, it returns 0. Can you think of a programming language which operates like this? Yeah. That would be great. If you have a programming language which operates like this, then this language must be able to determine whether something is defined or not. Or in other words, whether something terminates or not. If it terminates, it returns 1. If it doesn't terminate, it returns 0. Now this problem is called the halting problem. So in order to execute this, the computer first has to solve the halting problem, and after solving it, it returns 1 or 0. Now the halting problem is not computable. So this is a non-computable function. This is one of the functions that we don't want. This is one of the functions we don't want to include in domains because it's not computable. So there is no single programming language which can compute function f3. So function f3 is not computable because in order to find out whether the argument is defined, in order to find this out, the computer would have to solve the halting problem. So the halting problem is the problem, given an expression, you have to find out whether it terminates or not. And then after finding this out, you can do something else. And here you then return 0 or 1. The computer would have to solve the halting problem, and this is the most famous non-computable problem, solve the halting problem. So when we define the domains for functions, we want to exclude functions like f3. Exclude functions like f3 from our domains. And in fact, this function does not have these properties. So we want to look at monotonic and continuous function, and this function is neither monotonic nor continuous. And I will show you this in the next lecture on Friday.